Hello everyone. Today I'm just going to go through an introduction of using slope deflection method to solve for an indeterminate structure, which means that equilibrium equation is not enough to find all the support reaction. So in this video, I'm just going to go through a theoretical concept of how do we use this slope deflection and where we get this derivation or the equation. So the final equation for slope deflection equation is MAB. Here is given MAB, which I'm going to explain what does it mean. MAB is 2EI divided by L, 2 theta A plus theta B minus CEI delta L square plus fixed end moment. FEM means fixed end moment due to the external load. So we are going to see how do we derive or how do we get all this final equation in this video. So the first thing we need to know about the slope deflection is the assumption. We assume that there's no axial and shear deformation. So there's no that we expect that the beam will not have any axial deformation and also will not have a shear deformation, which means that the beam will bend due to its bending moment only. So which is the beam theory. Which is the beam assumption for the beam theory. So let's say that we have a simply supported, and we have a beam with a pin connected, and then we have a internal support of roller, and let's say that this is your A and this is B, and let's say that there is a general loading applied, and we'll say that this general loading is W, and then we also have a point load P, and we also expect that the settlement A will settle, or support A will settle, have some settlement, and B also will have some settlement. And if we have to draw the deflection of this beam, because this beam did not move, so they will stay as it is, and the support A and B will settle by some settlement value. So the whole beam will displace in this way. Okay, so that's how the beam will displace. And so what we are going to do is we're going to focus only on the section AB. We'll focus on this beam section AB. So we'll draw it, the beam AB. We have A and we have B, and we know that this will subject it to a load uniformly, not uniformly, but distributed load, and then we also have a load P, and this is the length L, and we know that joint A will settle over there and joint B will displace over there. And we're going to apply, remember that in slope deflection we are interested in the moment at A, and in slope deflection, if it is counterclockwise is positive at the joint, and if it is clockwise is negative. So we are going to apply a counterclockwise, a positive moment MAB. MAB means moment at a joint A in a beam B, and moment at a joint B of a member AB will be MBA. So we're going to apply a positive moment. This is different from the internal moment of a beam, which we talk about bending beam like siding, hugging. But here we are talking of a moment at a joint A. So MAB, this is different from MA or MB. So MAB means moment at the joint A in the beam AB, and MBA means moment at joint B in a beam AB. So in this case, we are going to apply a positive moment for each joint. And once we have the once we know that the point B will be displaced around here, and point A will displace quite below B, and so the final this is how, because of this, if you look at how the beam moments are applied, so we know that the whole displacement will be uh, it should be like a sine wave. Okay, so that's what we get. And if we draw a straight line between A and B, that is called as a chord, and we'll say that this chord, this is the original displacement with respect to displacement, and that will call us chord angle. And with respect to horizontal, that will be chord angle. And this is called as elastic curve, which means that it is linear, it is in the elastic range. And then if we draw a tangent to point A, will that angle will call it theta A. And if we draw a tangent to point B, and this angle from respect to the horizontal will be tangent or slope B. And then here is a relative displacement delta. We are interested in the relative displacement, not the absolute displacement. So we have seen that the absolute displacement is here, and absolute displacement for B is here. So the relative displacement will be the difference between these two. So this will be your relative displacement. So that's what exactly we draw over here. So now in slope deflect equation, what we are interested to find is what is A, B, which is moment at each joint. What is it's a function of your theta and your delta. So that's and your theta and your um, external load. What does it mean? It means that this moment at A will be affected by the load applied, and also will be affected by this slope or angle, and also will be affected by this uh, settlement. So that's the concept here. It's slope deflection. So and I find a relationship between the moment at each joint due to the slope, due to the settlement, and due to the external load. So that's a basic idea of slope deflection method. And how do we do that? Before we go into a slope deflection method, we also need to know about the degree of freedom. As you can see, all these are this delta and theta are the degree of freedom. That means each joint, can they move up or can they rotate? And again, make sure that we always follow this assumption: no axial and shear deformation. So what does it mean by degree of freedom? So let's say that you have a simply supported and a pin joint and a roller, and if you're applying a load P, we know that this beam will behave in this way. So in this case, we know that this is theta. If this is A, B, and this is theta A, this will be your theta B. So we say that because this at a joint A, it's always a node is considered as a joint or support or the end of member. So in this case, this is node A. Node A has 1 degree of freedom, and node B has 1 degree of freedom. So we say that this total system will have 2 degree of freedom, which is theta A and theta B. Since there is no settlement, so we don't have to consider the delta as a degree of freedom. And then what if you have a fixed end and a beam, and then if you apply a load, and we know that this is how it will be deflect. It will be straight line, slope has to be 0 at the fix, and then after that it will be rotating. So this rotation will be B. This is A, B joint, this is A joint. So in this case, we have only one rotation. So this A has 0 degree of freedom, and node B has 1 degree of freedom. So this will be 1 degree of freedom, which is theta B. And then let's say that we have, what if we have a overhanging beam. Let's say that's A, B, C. If you're applying a load here, this is how it will deflect. And because there is no actual deformation, so we know that there's it can only happen only one vertical um, deflection. And then this will be your theta C, and this will be your theta B, and this will be your theta A. So we see that at node A we have 1 degree of freedom, and then at node B we have 1 degree of freedom. At node C we have 2 degree of freedom because it has theta C and delta. So we say that this will be 4 degree of freedom. It means theta A, theta B, theta C, and delta. So this will be your degree of freedom. And then what if you have a frame? This is called as a non-sway frame. Non-sway frame means it won't sway. That means this joint or this spin, so you cannot move to the left or you cannot move to the right. So in this way, if you're applying any load, this is how the final deflection will look. So you'll see that node A has 1 degree of freedom, node D has 1 degree of freedom, node E has 1 degree of freedom. So the whole system will be 1, 2, 3. So we say that all this node has 1 degree of freedom. So this will be a total of 3 degree of freedom. Remember that um, node A is fixed, so it doesn't have any degree of freedom. Node B is fixed. So you have one node, two node, three node, 4 and 5. But you can see that in this one, it has only 1 degree of freedom because it can only rotate. This also can only rotate 1 degree of freedom, and this joint also can rotate. And this is, remember that this is a rigid joint. If it's rigid joint, your angle should be 90 degree even after loading. And then we call a sway frame. So a sway frame, that means it can sway. That means it can slide. So in this case, if we remove the joint C with a roller support, then you'll see that if you're applying a load, it will move by the same distance. And because we consider that there's no actual deformation, so that means the deformation, they will be the same. So then this all deformation will be the same. So all, even though it move, but because they have the same deformation, so we consider only 1 degree of freedom. So joint C will be having 2 degree of freedom rotation, because you can see that it can rotate and it can slide. And then joint D will have only 1 degree of freedom. And you can say, what about the deflection? It's because it's equal. If it's equal, then we don't count it twice. So 1 degree of freedom, joint E has 1 degree of freedom. So total will have 4 degree of freedom. So this frame has 4 degree of freedom, which is delta C, theta C, theta D, theta E, and the delta that you can call as delta CX. And you can see that these are the same. So basically you don't have, there will only be 4 variable in your slope deflection. So that's how you calculated the degree of freedom. And degree of freedom generally tells you the idea of how many variable will be there in your slope equation. If 1 degree of freedom, that means theta B will be the only variable you'll have in your equation. If 2 degree of freedom, that means theta A and theta B will be the only variable. If 4 degree of freedom, then you'll have all these 4 variable. And similarly with all this degree of freedom for the non-sway and the sway frame, then you'll have additional variable for the sway frame. So now once we understand the degree of freedom, now we can see the correlation between the slope, which is your theta, and moment relationship. And here we say that this is, let's say that you applying a moment MAB in your roller support, and this caused the beam to have a slope theta A, and this is fixed. And if you're applying a moment MAB, so there will be also the same rotation. It will cause the same rotation uh, that will resist the moment, which we call as MBA. So MAB, due to the applied MAB, we know that it will cause an moment at the support at the fixed end B. So now we wanted to find what is the relationship between MAB and MBA, and also what is the relationship between MAB and theta A, and similarly what's the relationship between MBA and theta A. So this is called a slope moment relationship. So in this case, the concept behind deriving this equation is we use the concept of uh, splitting the member into a determinate structure and then use conjugate beam theory. So how do we split into a determinate structure is by converting this into a determinate structure which is your simply supported, and then we apply a moment MAB, and this will be your reaction. And if you remember the bending moment will be, because this will cause uh, negative bending moment to the beam, so your bending moment diagram will be a negative one, which is MAB, and we can divide that, assume that EI is constant, so that will be your bending moment diagram. And then we'll use superposition because we just convert them into a determinate, so it has to be we use a concept of superposition. So we'll have another simply supported beam, and this time we'll apply a moment MPa, and this will be your reaction. And if we draw the bending moment diagram for this beam, will be again a right angle triangle, and will be plus, and this time will be MPa and divided by EI. Once we have get the bending moment diagram or M over EI diagram, I'll say M over BMD or M over EI diagram, we'll use the concept of conjugate. If we this is an actual beam, and if you have to draw the conjugate beam, then this will be a roller support and this will be free, and then the load applied will be um, the BMD diagram will have negative. Negative means the load will be pointing downward, and this will be MAB over EI, and then this will be your bending moment diagram MBA, but positive means the load will apply upward, so you have MBA over EI. And now we know that in a conjugate beam, your shear force at A in a conjugate beam will be actual equal to the slope in the actual beam. So shear in the conjugate beam will be equal to the slope in the actual beam, and displacement or um, uh, settlement in the conjugate beam will be equal to the displacement in the actual beam will be equal to the moment in a conjugate beam. But here we are not interested in the displacement, so we are interested in the slope. So all we need to do is we need to find the relationship between theta A, MAB, and MBA. So for that, if you take a moment about A, and then you calculate, and then you use the take a moment about A, so you'll see that if you take about this is A dash, B dash, this is just to represent that these are all conjugate beam. If you take a moment about A, so you know that this stress stress or no, load distribution will cause a counterclockwise moment, and this also will cause, and the other load will cause a clockwise moment. So MBA will cause a counterclockwise moment, and MBA or MAB will cause a clockwise moment. So that's what we did here. We have the MBA will cause a counterclockwise. So this is a counterclockwise moment, and then this is clockwise moment. So clockwise is negative, counterclockwise is positive. We have used this sign convention in when we solve any beam problem. And then once you have that, you'll find that the equation MBA is equal to MAB. This is very important, especially in your FE conceptual. It'll ask you that if we have this beam and you're applying a 5 kilonewton meter, what will be the moment carry forward or carry over to the fixed end? So how much of the moment will be carried forward to the fixed end? If you use this concept or this formulation, it will be 2.5 kilonewton meter. Okay, so please make sure that this relationship is very important. If the fixed end is fixed, if the one end is pin, one end is fixed. So if you're applying any moment of 5 kilonewton at the pin connected joint, it will carry over by 2.5, which means half of the moment will be carried forward or distributed to the fixed end. And if you have, however, if you have a simply supported and you're applying a moment 5, then this will be 0. There will be no carry over of the moment applied to the roller joint. Okay, so please remember that this is the thing that they may ask you in your conceptual question, and they ask you in your FE. So once you have this relationship, if you take again summation of all the forces moment about B, you'll find that you'll have a final relationship between theta A and MAB. So this will be the, if you rearrange all the terms MBA and MAB using this relationship, you'll find that this is MAB and this will be MBE. And you'll see that because if you separate it out, you'll see that 4EI over L theta A, you can say that this is your flexural stiffness. Okay, this is different from your flexibility coefficient. This is flexural stiffness, which means that what it basically says, it means that the k theta A over A means that k theta flexural stiffness of the moment at A due to unit rotation at A, and this will be moment at B due to unit rotation at A. So those are the flexible stiffness coefficient. Okay. So if you put all the equation, you'll find that MAB is equal to 4EI over L theta A and MBA is equal to 2EI theta A. And if you swap the end condition, which means that you're going to put joint A as fixed and then joint B as a roller support, and then we're applying a positive moment MBA. Remember that this is B, and then we know that this will also cause MAB at the end. And because of this, we know that this will be deflected in this way, and this will be your theta B. And we use, if we use the same concept of drawing the bending moment diagram using conjugate, you'll finally find that MAB is equal to 2EI over L theta B, and MBA is equal to 4EI theta EI over L theta B. So that will be your final relationship between theta A and theta B in a beam. And please remember that we always follow sign convention. We know that this is all counterclockwise. So that's your relationship that we get between the slope and moment relationship. Okay, so using the same concept now for the for how do we do the relative deflection, we know that just join A and join B, join A and join B. If there's a relative displacement by delta and we rotate it in, or we apply a positive displacement, how do we know the positive displacement is the chord rotation? If the chord rotation is counterclockwise, counterclockwise, then your relative displacement will be positive. So we see that all the chord displacement chord rotation will be counterclockwise. That means it is positive. So that means this displacement also is positive. And then if you once you shifted the if there's a settlement in the support, in a fixed support, we know that there will generate a moment. So that this is the actual moment that will resist due to the settlement. Okay, so once you have that, once you calculated all the displacement, we the moment at AB generated due to this displacement, and we already draw the correct correct moment, and you can correct you can use the same concept into a, you can divide this as superposition into a moment distribution method for simply supported with moment MAB. And if it is moment MAB, we know that that will create a positive moment, and for MAB over EI. And then for simply supported with just MBA, it will create a negative bending moment, and that will be MBA over EI. And if we use the concept of conjugate beam, it will be just free end at both end, because in conjugate, if it is fixed in actual beam, then it will be free in the conjugate beam. So this will be your conjugate beam, and the load distributed over the conjugate beam will be the M over EI diagram. So is it positive? That means it'll point upward. Then you'll have MAB over EI, and then this will point downward because it is negative, and this will be MBA over EI. And because both n are fixed, so we assume that both moment will be the same. And if both moment will be the same, we can take this is a dash, this is b dash, we can take, and this also, because there's a displacement, remember that this is a positive displacement, so moment also will be positive. So moment in your conjugate beam will be equal to your displacement or settlement in the actual beam. And once we have that, we can calculate all the relationship, summation of all the moment about b dash. We'll find that all the equation, and you'll see that this actually will give you m, from here equation will give you mab, and it will give you mba, which is equal to 6ci delta l square. Okay, so if you look at this, this is a equation, this is positive. Why it is positive? If you look at the direction of the bending moment that we that it generated due to this bending moment direction generated due to the settlement, it is clockwise. Okay, but we want to be consistent with the formulation. We want to make sure that all our formula or all our moment relationship with the slope deflection must be consistent in the sign convention. So if we make it into a counterclockwise, then it'll become negative. So that's why you have this final equation: MAB is equal to MBA is equal to negative 6CI L square into delta. So this is the reason why we have negative. If you solve this actual calculation, you will get a positive. The reason it's positive because if you look at the calculation here, it is MAB is counter clockwise, MBA also is clockwise. So that means if I want to make it counterclockwise, then this has to be negative. So that's a relationship between this relative displacement and the moment. And now finally, we wanted to find what is the moment generated or caused at each joint due to the external load. So this is called as also called as fixed end moment due to external load. And we use the same concept. We know that the simply supported with a P will be a triangle, which is PL over 4, and we'll divide that by EI. Assume that EI is constant. And remember that because you're applying a load P, this beam will trying to deflect downward, and so your resistance moment will be will resist that applied load, so it'll be counterclockwise, and this moment will be clockwise. So once we have that, we can if we draw the bending, the simply supported with just MAB, we'll get a right angle triangle, which is MAB over EI, and this will be negative, this will be positive. And then for MBA, it will be the right angle triangle, negative, and MBA over EI. And if we want to draw the conjugate beam, then we know that for conjugate beam, it'll be both and free, and you just have to, now the BMI M over I diagram will be your load distribution for a conjugate beam. And negative means downward. This will be MAB over EI, and this will be PL over 4EI, and this will be MBA over EI. And we know that the moment, again, it will create the same moment, so we know that MAB equal to MBA. So we take the summation of all the forces is equal to 0. You'll finally find that this relationship MBA and AB. Okay, and you'll see that because they are equal, again, because they are equal, you'll see that MBA, sorry, will be equal to, should be equal to PL over A. Sorry, PL over A, because we just said that this will be equal. So if this is equal, then MBA should be equal to PL over 8. But if you look at how the moment direction is, MAB is positive and it is counterclockwise, which is what we want. However, MBA is clockwise. So MBA is clockwise and it should be positive. But if we want to make it counterclockwise, then it'll become negative. So that's why you have negative. So finally, using all this equation that we already derived from for MBA due to the slope, MBA due to the displacement, and MBA due to the uh, external load, we can finally write the sum all of them, or you can combine or group them together. You can finally find that MAB is equal to the moment generated due to the slope, moment generated due to the deflection, and moment generated due to the fixed end moment due to external load. And similarly, MBA will be 2ei theta plus 2 theta b, and it will be the same displacement and fixed end moment PA. So this will be positive and this will be negative. Please remember that this will be positive and this will be negative. That's what we have find here. So with that, and also remember that we neglect the axial deformation, and sign convention is if the member end, the end rotation and chord rotation are positive when counterclockwise. So that is the sign convention. Many of the textbook will be using different sign convention. It could be confusing. So we wanted to follow one sign convention because we already started from the beginning of the class that the counterclockwise rotation is at the joint for a moment is positive. So we'll stick with that same consistency with the sign convention. So counterclockwise will create a positive moment, and that's what we're going to use here. So what it means that all this moment that we generated here is counterclockwise, and if we get negative, then it means that it's just clockwise. So that's how we generate, that's how we derive all this equation or relationship between the end moment MAB in terms of the slope, in terms of the settlement, and in terms of the external load. So with that's the whole introduction or whole theory of behind how do we get into the slope deflection equation. So in my next video, we are going to use this concept and apply in the indeterminate beam to solve all the support reaction. Thank you.